Good afternoon and welcome everyone. Thank you for being here for CCST's Expert Briefing on the Future of Gases. My name is Sarah Brady and I'm the Deputy Director at the California Council on Science and Technology. I'd like to open our briefing today by acknowledging that I am presenting to you from the tribal land of the Nisenan people. Sacramento was a gathering place for many local tribes. We acknowledge the southern Maidu people to the north, the Valley and Plains Miwok peoples to the south of the American River, and we would also like to acknowledge the Patwin Wintun peoples to the east of the Sacramento River. Today, I'll briefly introduce CCST, our Disaster Resilience Initiative, and quickly hand it over to our moderator and expert panelists. The California Council on Science and Technology is a nonpartisan, nonprofit organization established over 30 years ago at the request of the legislature. CCST was created to provide science and technology advice from the wealth of outstanding academic and research institutions in our state directly to policymakers. California is quite lucky to have such an incredible network of expertise. And our job at CCST is to help amplify and translate the expertise in this network into actionable advice for policymakers. We do this through a number of mechanisms, including expert briefings like the one you're attending today. We host workshops and develop peer-reviewed technical reports. And we run the CCST Science Fellows program, where we place PhD scientists and engineers for a year of government service and leadership training in the executive branch and the legislature. As part of our mission, CCST recently launched our Disaster Resilience Initiative to help the state better prepare for and respond to ongoing, complex, and intersecting disasters. These include climate change, extreme heat, power outages, and the ongoing COVID-19 pandemic, which are all radically disrupting the ways in which Californians live and work. And while these disruptions are often destructive and painful, they also provide us opportunities to redesign our systems to be more resilient and sustainable. Through our Disaster Resilience Initiative, we seek to deliver science and technology advice to reduce harm and improve the lives of all Californians. Today, we'll be focused on how carbon neutral gases can help California meet its climate and disaster resilience goals. I'd like to introduce our moderator, Dr. Jack Brouwer, Professor of Mechanical and Aerospace Engineering and Associate Director of the National Fuel Cell Research Center and Advanced Power and Energy Program at the University of California, Irvine. He is a nationally recognized expert on renewable energy systems and hydrogen and electricity infrastructure development. Welcome, Dr. Brouwer.
Thank you very much. It is my pleasure to speak to you today about a topic that we have been studying here at UC Irvine for a very long time, and that is how can we achieve zero emissions of greenhouse gas and of criteria pollutants. And increasingly, that means that we have to depend on solar and wind power and other primary forms of energy that are renewable. And these, however, must be complemented by energy storage and dispatchable generation resources that can enable that zero emissions future to also be resilient. And that's what we're talking about today. The state of California has already passed laws to force carbon neutral resources to supply all of the electric grid by 2045 and to achieve net zero CO2 emissions and negative emissions thereafter. And these systems are going to require carbon neutral gases like hydrogen and biomethane or other biogases to engender all of the characteristics we need in society. And we're not the only ones that have realized that. Many jurisdictions around the world, Germany, France, Portugal, UK, Japan, Australia, they are all leading with regard to implementing the policy framework and the actual technologies to enable these carbon neutral gases to complement sun and wind power. So today I have with me 4 experts working on current and emerging technologies to produce and use these carbon neutral gases to help California meet its zero emissions policy goals. So our first panelist is Dr. David Blekhman, and he is a professor in the Department of Technology at California State University, Los Angeles. Dr. Blekhman, please.
Thank you, Dr. Brouwer. I look forward today to share my vision. So my name is David Blekhman. I'm a professor of technology at Cal State LA, and I'm also a founding member and the technical director for the Hydrogen Research and Fueling Facility. And at this facility, we are looking at providing operational research and also workforce training at the bachelor's level. As a faculty, I was also responsible for the establishment of the largest EV charging infrastructure in CSU system that includes 6 fast chargers. I was a lead advisor for EcoCar 2 and EcoCar 3 competition, where we converted full-size cars into hybrid vehicles for the competition. At the hydrogen station, we organized a shared mobility program with 17 fuel cell vehicles used by students and faculty before COVID times. I also was responsible for building our own solar system on campus, and a small one for student learning, but now it has been followed up by a 1 megawatt solar system built by the university. Hydrogen at Cal State LA Hydrogen Station is produced via electrolysis using just water and renewable electricity from our solar system. With that, we can observe the complete cycle from renewable energy generation to producing green hydrogen and to the end user or to the vehicle. In this briefing, I would be happy to share my vision for California regaining its leadership in hydrogen technologies, use of California funds to attract federal funding. Also, I would like California to engage in multi-state projects. This can be enabled by creating a complete multi-state hydrogen map and use funding to strategically fill in pieces on this map. We see such plans already developed in Europe and around the world. So let's bring it back to United States, to California. Thank you.
Thank you very much, David. And our next speaker is Dr. Hanna Breunig, research scientist in Climate and Ecosystem Sciences Division from Lawrence Berkeley National Lab. Dr. Breunig, please.
Hi, everyone. I'm really happy to be speaking on this panel today. I'm a research scientist in the energy technologies area at the Lawrence Berkeley National Lab and deputy head of the department called the Sustainable Energy and Environmental Systems Department. In this group, I lead work looking at cost assessment, life cycle assessment, looking at greenhouse gas emissions and criteria emissions from early stage technologies to understand how to work with early stage scientists developing the technology to better scale their systems for when they're going to be deployed in the real world. I also look at process models to understand how the coupling of these systems with our current electricity grid, energy systems, and end uses of these energy systems can be improved. I started my work in this space at Cornell University, looking at dedicated energy crops for bioenergy. But since then, I became very interested in the use of organic waste for making carbon neutral biogas, hydrogen, methane, and other gases like syngas that can be used in our system to offset the use of fossil fuels, along with the capture of carbon dioxide from these systems to even go negative when we think about life cycle greenhouse gas emissions. Over the last 4 years, I also have done work for the Department of Energy looking at hydrogen, the generation of hydrogen, as well as the storage and transportation of hydrogen, comparing very early stage technologies that use novel materials for the storage to do a better job than what we currently have when we're thinking about transporting hydrogen with compressed systems and liquefied systems. Thank you.
Thank you very much, Dr. Breunig. And our next speaker is Dr. Chris Marchi. He is distinguished head member of the technical staff in the Hydrogen and Material Science Group at Sandia National Labs. Dr. Marchi, please.
Thanks, Jack. So as Jack said, I'm Chris Marchi from Sandia National Laboratories in Livermore, California, and I'm representing our hydrogen program here in Livermore. This is a program that's principally funded by DOE, but not exclusively. And our program is built around the H2 at scale vision. If you're not familiar with the H2 at scale vision, this is a vision from DOE imagining what the future energy system looks like and the intrinsic role that hydrogen can play in that system, all the way from production to delivery to utilization. Hydrogen is a very flexible molecule. It can be produced by a number of different ways. And so this vision imagines using nuclear power, for example, to produce hydrogen, imagines using curtailed wind and solar, or even direct conversion processes such as concentrated solar to produce hydrogen. Really a portfolio approach to hydrogen production, given its incredible flexibility. And on the delivery side, for example, considering our natural gas infrastructure, hydrogen is a gaseous fuel, much like natural gas. And there's plenty of experience in industry for distributing hydrogen using similar kinds of methodologies that we use for natural gas and other fuels. And then in the utilization space, hydrogen, again, is very flexible, and there's a lot of opportunity for hydrogen across our utilization. And the other key component that H2 at scale envisions is enabling decarbonization and the integration of our energy sector. So hydrogen can be used as transportation fuels. Many people in California are familiar with this, the fuel cell vehicles that are on the road today. But there are many other uses of hydrogen potentially. So hydrogen can be used in the power industry. For example, it enables dispatchable loads on our grid by using electrolysis that can be distributed. You can also produce electricity from hydrogen using fuel cells. So this really becomes a methodology that you can support the grid and add resiliency, which enables our energy response, for example. And then in industry, hydrogen can be used to decarbonize difficult sectors where it's very difficult to remove the carbon, for example, in cement making, steel making, and glass making. My particular expertise at Sandia is in the area of materials compatibility and safety. So I do a lot of work trying to understand better the effects of hydrogen on materials, the structural integrity of things like pressure vessels at fueling stations and pipelines where we might be distributing hydrogen. It's a pleasure to be here today, and I look forward to an enjoyable conversation.
Thank you very much, Chris. And our last speaker is Dr. Katherine Rinaldi, researcher in chemistry and chemical engineering at Caltech. Dr. Rinaldi, please.
Thanks so much, Jack, and thank you to the CCST for organizing this panel and giving me the opportunity to be here today. My name is Katherine Rinaldi. I just completed my PhD under the advising of Nate Lewis at Caltech, where the bulk of my work focused on looking at the role of hydrogen in renewable energy systems from both a technical and systems approach. As a part of a collaboration with Ken Caldera at the Carnegie Institute, our group has used multiple decades of historical wind and solar data to understand weather variability and its effects on renewable electricity systems. In particular, and I think most relevant to our discussion today, I was involved with work led by another graduate student, Jackie Dowling, which demonstrated that when we add long-duration storage technologies, such as hydrogen storage, to 100% reliable wind, solar, battery electricity systems for the contiguous United States, that reduces costs at current technology costs. We found that more short duration storage technologies like batteries and long duration storage technologies like hydrogen actually have these complementary roles where batteries fill these intra-daily, hourly storage gaps, and hydrogen fills the seasonal and even multi-year storage gaps. And we also showed that when we reduce costs of long duration storage, that does more to reduce overall costs than reducing the cost of short duration storage like batteries. I then expanded on this work in another project by looking at weather behavior in California specifically. And we found that California actually experiences periods that we've termed wind and solar droughts that are essentially multi-day calm and cloudy periods over the whole state every year that really strictly limit the renewable electricity generation at those times. So when we compensate for lulls in renewable electricity generation due to these multi-day droughts, we need a carbon neutral or carbon-free fuel such as hydrogen, and that will enable California to meet its SB 100 and climate goals in a more cost-effective way. So I'm so happy to be here today, and I'm excited for the panel.
Thank you very much to all of you. And I'm going to continue with first names on a first name basis with all of you. Please call me Jack. Our first question comes from Senator Josh Newman, who asks, what is the path forward in terms of producing green hydrogen? May I ask David to respond first, please?
Thank you. This is an excellent question, how we approach and build out our renewable energy generation. I think the only approach is good planning. And, and that's what engineers and scientists do. So creating a full process where we have generation and we are not wasting that renewable energy. We want to create a next layer of technology that can take all of the energy and convert it to hydrogen or partially to the quick turnaround storage like batteries. And after that, we are going to develop hydrogen utilizing technologies. It could be in industry, and that would be a large consumer. Very good to reduce overall cost of hydrogen by having a large consumer. We can use then hydrogen for transportation and commercial applications, and also it will increase our resilience. So a good planning, a good hydrogen roadmap, and gradually filling in each solution that with the smart financing for each of the steps, for each of the pieces of the puzzle. Thank you.
Hanna, can you add something, especially focusing on the bio pathways, perhaps?
Sure, yeah. I think one of the key aspects for both bio pathways and water electrolysis pathways is to de-risk the deployment of it by ensuring that there are markets. So ensuring that infrastructure that's developed will be compensated for regardless of the number of vehicles that are using hydrogen on the ground today. Once that's in place, they'll be able to profitably generate hydrogen using local resources and creating local economies. Bioenergy is particularly useful for this because you can harvest bioenergy from local areas and provide a steady, firm supply of resources to generate that hydrogen that is not dependent on weather. This is very important for empowering local communities, but it also requires the involvement of local communities to help scale this and tell them what the benefits and potential risks are very transparently, as well as how to mitigate any potential risks in that area. I think this is very important for coupling bioenergy to the hydrogen scape. And I think in addition to developing new infrastructure, we have to think very creatively about how to use existing infrastructure. For example, bioenergy facilities are sited in certain locations for certain reasons. Maybe we can leverage that decision-making to help scale up hydrogen quickly. Thank you.
Thank you very much. Nice points. Chris, can you add anything to this, please?
Yeah, sure. So I think we really need to think about this from a portfolio perspective. Different regions have different resources. And one of the advantages of hydrogen is it's very flexible and you can produce it from many different types of technologies, including the biomass pathway that Hanna mentioned. So I think we need to think about this holistically, regionally, and with a portfolio perspective.
Thank you very much. And Kat, do you want to add anything?
Yeah, I mean, I think everyone touched on it well. I think really to make green hydrogen possible, you need cheap renewable electricity and you need cheap electrolyzers. And people have touched on it a few different ways to get those. One related thing I wanted to bring up, something that we work on in my lab at Caltech, is that a lot of the catalysts in the electrolyzers that are used today, as you know, are made from expensive, scarce metals like platinum and iridium. So when we think about scaling up hydrogen to the kind of levels that we're talking about, we need to think about developing cheaper, more abundant catalysts, because these expensive catalysts will pose both the supply chain problem and potentially a geopolitical problem because they're in such few countries worldwide. So the development of cheap catalysts, I think, will aid in this as well.
Very nice set of points. Thank you very much. I also agree that we need to have a firm and established policy framework in which we can count on that policy to always be in place between now and then, so that we can actually finance these kinds of projects going into the future, right? So that banks can trust companies to advance these technologies and then have them come down that cost curve that we know they will come down, just like sun and wind power did, and batteries. Our next question comes from Larry Basket. What are the key technology and infrastructure hurdles for hydrogen power use? Hydrogen embrittlement of metals, or the power required to produce it, or the energy conversion technologies, et cetera. So what are the key technology and infrastructure hurdles? Maybe I can start with you, Chris, please.
Sure, I think so. A lot of people talk about the embrittlement problem.
Yes.
But I think that is a problem that is surmountable. I don't think it is a roadblock by any stretch. We need to understand our systems and design accordingly, but I don't think it's a roadblock. I think the biggest challenge, as Katherine pointed out, is production and the cost of things like the catalysts that are needed if you're using electrolysis, for example, to produce hydrogen. It's really at present, it's the cost of production of hydrogen, which seems to me to be the biggest hurdle to rolling out hydrogen technologies at a much grander scale.
Yeah, very nice. Hanna, you want to add something?
On the bioenergy side, hydrogen can be generated using a gasification technology. So that without combustion, taking organic matter and using some oxygen and gasification, converting it to hydrogen, carbon monoxide, which makes a syngas. This can then be used to generate energy. So one of the challenges here is making sure that this system is being scaled to the level of the biomass available. So this is still requiring demonstration to prove the technology's performance. It's been demonstrated many times for coal, and now we need to demonstrate it at scale for solid, dry, or low moisture biomass. So this is very critical to demonstrate this and demonstrate the air emissions generated from these facilities.
Yes, both biomass and some waste streams are amenable to this type of conversion to either hydrogen, or even taking that synthesis gas and making liquid fuels with further processing downstream. This may be a very important way in which we can use these kinds of biomass facilities. I also think it's quite important to note that in our own analysis of the California roadmap for achieving renewable hydrogen in California, this was the cheapest way to make hydrogen. I'm not sure that that's going to bear out, but that's what we analyzed in our white paper. How about you, Kat? Anything to add there?
I guess I would just add for these infrastructure changes that are expensive, like we've been talking about, it's really important to be in a regulatory framework that incentivizes this in-state research and development and manufacturing of green hydrogen now during this transition period where it's still more expensive but less polluting than fossil fuels, so that we have it ready for when we need it to meet the regulatory requirements of the SB 100 and bills like that.
Yes, thank you very much. And David, anything?
I think the major roadblock is commitment. What I mean by that is that unlike batteries, for example, every country, almost every country can be contributing to the hydrogen economy one way or another. It's not limited to the mining in one country or processing in another country where only a few countries benefit. Hydrogen has a broad opportunity for benefits. And so it's just a matter of commitment and getting those maps, getting those plans drawn and move forward. Additional point I would like to make is, syngas or production of hydrogen from natural gas. We have experience with this, we have multi-year experience with hydrogen. And I want to highlight that it's not a new product for us to work with. Hydrogen has been used for many years now. For the space program, we learned not only gaseous hydrogen, we know how to deal with liquid hydrogen, and with the science from our material scientists coming forward, we can utilize all of these experiences and start hydrogen economy. It doesn't have to be starting just as a trickle on the renewable side. We can build a lot of pieces using reformed hydrogen and renewable hydrogen together to build this economy in large applications and large use cases.
Yeah, we can do this. We just need to commit to the known zero emissions vector of hydrogen and renewable gases. Okay, our next question comes to us from Nicole Cropper, Special Assistant to the California Public Utilities Commission. She asks, what sort of equity considerations do you think are particularly important to keep in mind for hydrogen development and deployment? Have any environmental justice communities been involved in some of these early research and planning discussions? And let me just say that on behalf of the National Fuel Cell Research Center here at UC Irvine, we have definitely engaged with communities in the Wilmington-Carson area that are disadvantaged, certainly. And we have been engaging with them to help understand what their concerns are first, but then to also talk to them about the potential for hydrogen to decarbonize, especially these heavy duty applications that are in these port complexes, that are in these main transportation corridors where you have heavy duty trucks and trains and everything going through. And so these sorts of things are especially amenable to hydrogen use for achieving zero emissions. And it's not only zero carbon, which is super important to these communities. They are suffering more from air quality and health impacts associated with that. So these are some of the equity considerations that we are personally being involved in and accomplishing. Anyone want to volunteer here for adding to that? You can just raise your hand. Okay, Hanna, please.
So on the bioenergy side, today we have an enormous amount of our waste being burned in agricultural practices. We have wildfires we have to worry about. We have landfills we have to manage. And while there are some concerns about odors and air emissions from these early stage bioenergy conversion facilities, there are projects ongoing right now working with local communities to understand and mitigate those through just simple fixes, such as improving the biofilters being used at these facilities. So there are opportunities to make sure that the technologies replacing the current end use of bioenergy are going to serve the community in an even better way. There's also really important considerations around the end use of hydrogen. When we think about industry, we have to think about where the added price goes. So when you're making them use a more expensive fuel, you have to consider what that's going to do to the price of that. And how does policy serve to control that so that doesn't trickle down to the users? There's also an issue around the number of cars today and who can afford expensive hydrogen cars. So there are opportunities to make this technology available to low-income families through buyback of cars. There's many concepts that are very exciting here that can also be applied to the hydrogen world.
Very nice. And we have the good fortune of working with a disadvantaged community here in Huntington Beach, California. Yes, there are disadvantaged communities in Huntington Beach too, to figure out ways in which they can be have access to things like solar, even though they live in rented places, or access to even low to LED lights and things like this, which aren't very common in their neighborhood, which is very unfortunate. I saw that David raised his hand.
Yeah, I would like to bring another angle to the discussion is a workforce development. So Cal State LA is a minority serving institution. We work with students coming from East LA, Montebello, and all other disadvantaged communities. And having infrastructure on campus allows us to prepare that workforce in the solar and especially in the hydrogen industry, because we have internship program right at our hydrogen station. It's a limited program because it's just limited funding. We would love to grow it with more funds. And actually, I would like to compliment Dr. Brouwer for his graduates who are moving forward hydrogen industry, like company, for example, First Element, and our students at Cal State LA, minority students now working for that company. And we actually have a program now with First Element where they're interested in internships for our students. So
I really appreciate that.
Workforce development is another thing we can do for our students, for our disadvantaged communities.
Yeah, and interesting. Yeah,
new economy.
Yeah, and interestingly, if one adopts all of the above technologies for achieving carbon neutrality, you engender a wider cross-section of jobs. So now we aren't only looking for electrical jobs, we're also looking for pipe fitters and all sorts of others that can handle both the renewable electricity and the renewable and carbon neutral gas. Okay, so this is a really important feature that California can lead in. Any additional questions or comments? Yes, Kat.
Yeah, I just had one comment. It's just been shown that these disadvantaged communities are disproportionately been affected by disasters and things like blackouts. And so when we incorporate things like hydrogen, that's what we need to have an incredibly reliable electricity system. And so in adding it to our electricity system, increasing that reliability, we can aid these communities to prevent further blackouts or disasters that would disproportionately affect them.
Yes, absolutely. So making the grid more reliable to these disadvantaged communities can be engendered by these carbon neutral gases that we're talking about. Okay, anyone else? All right. Our next question is a question for Dr. Rinaldi, who was just speaking. Does the concept of drought in clean energy production include offshore wind in California, or does it only apply to land-based wind and solar?
Yeah, so the study that I did, we only looked on land-based wind and solar, primarily just because California has a really steep coastline, and also there's a lot of restrictions on the water side, conflicts with the military, and so there's a very small opportunity for the growth of offshore wind in California itself. So we just focused on onshore wind.
Let me say, though, that I have a current study that is addressing both onshore, offshore. It's building upon what you have already accomplished there at Caltech, where we're looking at offshore wind and adding it as a resource to the onshore and solar. And there still are energy droughts under those circumstances. Okay,
yeah, I would expect
it's not perfectly complementary, and the wind is still not always blowing over the ocean.
Exactly.
So it have and this is the same thing that other jurisdictions have found. Okay, for example, the northern UK, which is looking at solar, onshore wind, and offshore wind, and they're depending mostly on offshore wind because of the North Sea wind that they have a resource for, but they still have major droughts. Major Dunkelflauten, as they call it in Germany.
Yeah, I learned that word during the review process.
Which means dark lull, Dunkelflauten. And that's when you have both darkness, no sun, and no wind.
Absolutely. And when we just look at these very long time scales, you just have extreme variability in these resources. So there's always going to be periods where there's lows. I found even when I aggregated over the entire Western interconnect, there were periods where the wind was lulled. So even if you aggregate over really large areas, you're going to have to deal with these resource droughts.
So we have a question for someone close to your heart, Kat. This comes from Nathan Lewis. There seems to be an impression that California will just electrify everything. If so, then there is no role for hydrogen. What energy services critically depend on a fuel or gas that cannot effectively be provided by electricity, no matter how cheap the sun and wind power are? Does someone want to volunteer? Because I could volunteer too. Let me mention a couple of things. Long duration storage, because battery energy storage technologies have self-discharge, is better engendered by hydrogen energy storage. Secondly, massive energy storage. When the power amount is fixed, it's just the daily excess, okay? The massive amount of energy storage is engendered by the separate power and energy scaling characteristics of hydrogen energy storage. And this is not engendered by battery energy storage. You always have the same amount of power and energy that comes with a battery pack. If you need more power, you need more batteries. If you need more energy, you need more batteries. In hydrogen, you can size the tank for the energy separate from the energy conversion steps of electrolysis and fuel cells. So it's always going to be cheaper to do hydrogen than it is to do batteries for massive energy storage. And then we have some end uses like aviation, shipping, long-haul trucks and long-haul trains, some industries that require a reducing gas. How do you produce that with electricity? You can't. Or that require a feedstock like hydrogen. You have so many of these things. And if we want to decarbonize everything, we need hydrogen for these sorts of purposes. And they cannot be met by batteries or batteries plus solar and wind. And by the way, we should think of hydrogen as a vector of electrification, because most of the hydrogen in the future that we envision is going to be made from renewable sun and wind power. We are still going to have some from bioresources, but most of it's coming from sun and wind power. Others want to say something there. I probably missed a few things in that list I gave. Yes. Okay, we'll go with Hanna first.
Thanks, Jack. So one thing that's also really important that hydrogen can play a role in is disasters, backup power. So right now, we're required to have diesel generators at hospitals. That's because they want on-site fuel and on-site generation. So instead of just having a system that's delivering electricity or that's delivering hydrogen through a pipeline, a lot of data centers and microgrids and community services that are very critical to the health and well-being of not only the community, but the economy during a disaster, whether human-made or natural, requires an on-site source of fuel. Hydrogen can be an excellent solution for this. That so far we're having a great challenge just providing with batteries when we're talking about multiple days or times over about 10 hours.
Yes. Wonderful, Hanna. Thank you for that. And Chris, you raised your hand too.
Yeah, I was just going to re-emphasize something that you said about the storage. I mean, storage is key to making all of this work. I think we sometimes forget that fossil fuels are essentially storage, energy storage, right? We store tremendous amounts of energy as fossil fuels, whether it's natural gas in the ground or, petrol at the fueling station. So, if we're going to electrify, we need to also be thinking about replacing those. And as you pointed out very eloquently, hydrogen is a convenient vector for doing that.
Thank you very much. David.
Yes, a couple of points. I'd like to go back to transportation, which you mentioned, but I would like to detail a little bit. First of all, fueling with hydrogen is much faster, could be accomplished in 3 to 5 minutes. And if you're using fast charging on an electric car, it's a half hour. And imagine your second car. So you're out waiting for a whole hour for your 80% of the distance. Increasing distance with hydrogen is very easy. It's just a slightly bigger tank, and it doesn't add mass to the vehicle.
Right.
So it's a
lightweight, very lightweight.
Very lightweight, and same. Even if even though we see passenger cars kind of catching up to hydrogen, but not on fast recharging, trucks will not be able to survive economically if they just have to haul 20,000 pounds of batteries just to get from point A to B in their duty cycle or an expected delivery time.
Yeah.
So we see a lot of sectors critically dependent on hydrogen once we convert.
Yeah.
And another point, I already made it, but hydrogen universal economy developer. If we are electrifying everything, where all the funds will go? To the mining companies and to the processing companies, where with the hydrogen we can actually benefit economy of all.
Very nice. And I like your detailed points of anything that requires rapid fueling, long range, or heavy payload will prefer hydrogen for zero emissions. Thank you. Okay, and Kat, you wanted to say something too? Okay, you're good. All right, let's go to the next question then. And this comes from Iraj Urshagi. And he asks, how affordable is hydrogen compared to other fuels? Anyone want to take that? Or I could maybe add my first point. I'll add first. We have a hydrogen fueling station on our campus, just like Professor Blekhman does at Cal State University, Los Angeles. And we are currently selling for $14.50 per kilogram. Now you must understand that that corresponds because hydrogen fuel cell vehicles are 2 to 3 times, more energy efficient than a gasoline vehicle. So you divide it by about a factor of 3. And if you divide it by a factor of 3, it's almost the same price as gasoline today at $4.50 per gallon. And it happens to be that a kilogram of hydrogen is roughly the same energy content as a gallon of gasoline. Interestingly, in the very most modern stations, they're already selling for about $12 per kilogram. And we know that we can, in the future, make hydrogen much more cheaply than we are making it today. Most of our renewable hydrogen in the state of California is coming from landfill gas that is directed via pipeline to steam methane reformer units. And that's being then delivered to fueling stations and being dispatched. But we have looked at solar plus wind power, which are now the cheapest forms of primary energy, and followed their cost curves over time and looked at electrolysis and its cost curve over time. And we're not the only ones that are doing this. There's a whole bunch of jurisdictions all around the world doing this. And we know that in the future, we can make hydrogen at less than $1 a kilogram. This is also what the Department of Energy plans to do in 1 decade. This is what they declared in the Hydrogen Energy Earthshot announced not so long ago. $1 for 1 kilogram in 1 decade. And I know it's possible because our technical analysis have said this for many years. Now, hydrogen is more difficult to move around in society than our current infrastructure fuels. So we should expect that it's not going to cost people $1 because we can make it for $1, but then we still have to deliver it via pipelines and trucks and have to have fueling stations and all of this. But just imagine this. The renewable hydrogen future, I think, will be more cost effective than our current fossil infrastructure. I'm positive that this sort of change can be done and make it more cost effective for the same features. Maybe I spoke too long. Any of you want to add something to this? David, please.
So those are excellent points. And I think we have an issue of economy of scale at this point. The analogy would be that we are all driving Rolls Royces. It's a Rolls Royce hydrogen station because it's a custom built. It's a Rolls Royce vehicle because not many of them are built yet. And we have a Rolls Royce supply. And so each of the times, those are still very costly, but small plans. So once the economy grows so that the prices for gasoline will go down for hydrogen will go down, and hopefully drive the competition for gasoline down as well.
Yeah. Others want to comment on this? Yes, Kat, please.
Yeah, I just wanted to make the point again that California can't meet its regulatory goals without the fuel. And so regardless of the cost, we're going to have to incorporate hydrogen in order to meet our SB 100 goals. And in terms of reducing those costs, as Jack and David were saying, there's been progress in reducing the cost of hydrogen, and we expect to see continued progress when looking at hydrogen being used for energy storage for a wind solar battery system. We found that reductions in the power conversion costs, so reductions in the fuel cells or the potentially development of hydrogen combustion, 100% hydrogen combustion turbines, that would have a big impact on costs. And those are developments that are happening right now. So there's progress happening toward reducing the cost of hydrogen.
And it's complemented by international efforts that are doing the same sorts of things. And as a result, the cost curve is going to come down pretty quickly, I think. Others want to add? Okay, so the next question comes to us from Alfredo Arredondo. And he asks, when it comes to green hydrogen, does new evidence of ongoing mega droughts factor into the current thinking about the viability of using clean water as a source for the future, given that it will be in competition with other uses of a dwindling supply? It seems like the hydroelectric generation is being forced to grapple with that now. Anyone want to answer something with regard to water use and the challenges associated with that? Yes, Hanna, please.
Well, I can just provide some perspective that we have to think both about consumption and withdrawal. So when we're talking about generating hydrogen from electrolysis, we're talking about full consumption of water, even if that footprint is orders of magnitude smaller than the amount of water that's used at a coal power plant, or in steam reforming. With the withdrawals, the actual consumption is going to be something to consider. So this is something that can't be just ignored because it's less than the fossil fuel. That being said, it's not going to be a greater consumption than our golf courses. And so we need to think about our priorities here and be careful with drought, but also I think the footprint needs to be taken in context of current water use in urban areas.
Very nice. I don't want people to miss that point that you made in the very middle of that all studies that I have seen show that water use, okay, not necessarily withdrawals, this is a very important point that you make, but water use is going to be less than that which we currently use for our fossil energy conversion. Okay, Chris, you had a point.
Yeah, I just wanted to mention that there are folks working on electrolysis that runs on seawater, for example.
Yeah.
So this isn't necessarily just a burden on our fresh water. Potentially in the future, we'll be able to use things like seawater.
Very nice.
Or reclaimed water or.
Yeah, reclaimed water. Yeah, I agree. Yeah. David?
Well, actually, I've been looking at the other end of this problem. A fuel cell is a power plant that takes hydrogen and oxygen and produces electricity and water. And water comes out of fuel cell as a water vapor. And so the Metropolitan Department of Water and Power provided small fund, and we built a unit that can be plugged into a fuel cell vehicle and condense water. And we are recovering about 1/3 of water. So a little bit technical comment. When we are producing hydrogen, 1 kilogram of hydrogen requires 9 kilograms of water, but it's the same backwards. From 1 kilogram of hydrogen, we will be producing 9 kilograms of water. And our simple heat exchanger condenser unit was recovering 1/3 of that water from the vapor and nitrogen steam coming out of fuel cell.
Very, very nice. And I guess that corresponds to the virtuous cycle that some people call it of any kind of water conversion to hydrogen eventually results in its reconversion to water in the end. Now, of course, that's not the same as putting it in the ground. Okay, it takes a while before it replenishes the aquifers and gets up on the mountains and stuff, but the earth does that for us. So over time, it can be sustainably done. Okay. Any other comments on the water use topic? Very nice. So our next question comes from Iraj Urshagi. What are the risks associated with hydrogen storage? Maybe I can ask you, Chris, to talk about that first.
Well, so there's still some unknowns around large-scale storage. We store a lot of natural gas, for example, in geologic formations. That's one opportunity for storing hydrogen as well. But we don't understand how hydrogen behaves in some geologic formations. Things like salt domes are very well characterized and proven technology. And this is used currently already.
Yes.
And there's plans to build more salt caverns in Delta, Utah for the IPP program, which would store tremendous amounts of hydrogen. But we need to understand the storage problem more broadly so that we can take advantage of different types of geologic formations to store hydrogen. And so I think some of the risk associated with there is can we contain the hydrogen? It's a very small molecule, so it tends to get through everything. And so we don't know how well we can store hydrogen in some of these types of formations.
What about other forms of storage, like, for example, what we do on board vehicles? Are there risks associated with that?
Well, there certainly are risks associated with everything, right? I mean, on a vehicle, you're driving around with a lot of gasoline. So now you're changing that out for hydrogen. These systems are incredibly robust and incredibly safe. The carbon fiber composite tanks are astonishing in what they can contain. And one of the benefits of hydrogen is it's a very light molecule, and so it disperses very rapidly. Unlike other gaseous fuels like propane, which tend to sort of stay on the ground,
accumulate
on the ground,
at ground level,
and create a huge hazard in that case, whereas hydrogen will dissipate quite rapidly.
Yeah, so in the case of an accident or leak, it can be even safer than some other infrastructure fuels.
Right. I think, every technology has its own characteristics, and we need to plan and design for those characteristics.
Yes.
And there's no reason we can't make hydrogen technologies as safe or safer than the current existing technologies.
Thank you very much for that. Hanna.
So in our project looking at the coupling of hydrogen to the iron and steel industry, we're thinking carefully about how do you store that much hydrogen at a location. So not thinking about piping it in, which it could be an option, and therefore the pipes are the storage. And DOE has a hydrogen safety panel that can vet and work with us closely to understand how you apply analogs of regulations, safety, and codes and standards to these hydrogen systems. That could be everything from how much space do you need around a certain storage tank to deal with it. One thing that became clear in this study is that for a large scale industrial application, compressed gas just doesn't make sense. The footprint is going to be way too large. Cryogenic systems also are unlikely to make sense due to the large cost of cooling that much hydrogen. So now we're starting to think about material storage, where you can actually store the hydrogen at ambient conditions, so you don't have high pressure or low temperature systems. So those are chemicals that we can apply our current approach for any new chemical that's being introduced to understand what the mitigation of risk needs to be.
Yes, and interestingly, some of those same chemicals can have multiple uses, like ammonia, for example, which is a fertilizer in addition to it being a convenient way to store a lot of hydrogen at relatively low temperatures and pressures. Any last thoughts on that with regard to storage? Let me please then move toward last thoughts, final thoughts on this topic from each of you. And we'll go in the same order that we went in the very beginning, starting with David.
I would like to thank every panelist and every author of the question, because this is a very interesting discussion and brings a lot of important points for us moving forward. I think it's just a point of commitment. I think I discussed that. There are technical challenges, political challenges, legal challenges. And with this commitment, we can work through them, creating policy, proper investment, and good planning. That's what we need to do. And I really hope that this briefing could be used moving forward for starting a really good, strong planning process. Thank you.
Thank you. And Hanna next.
Thank you. So what I see is there's a clear role for science and technology, as well as very practical developments on the policy and regulatory side. On the science side, we need to understand how to drive down the generation of hydrogen and how to do it very energy efficiently with materials that are not going to lead to upstream consequences in their generation and end of life cycles. On the practical side, we need to demonstrate return on investment to these early stage adopters of this technology. And that will come from clear policy signal, as well as just getting some pilot projects out, not expecting their perfection, but expecting them to be very informative for how we go forward. Learning how to integrate hydrogen with other systems, such as the electricity grid, is not simple and not something we can just do on paper. We need to actually have some projects help lead the way and learn from those projects, understanding that we are learning as we are moving forward. Thank you.
Thank you, Hanna. Chris.
Yeah, I think policy is very key to the success of moving hydrogen technologies forward. One of the challenges that we face in our safety work is authorities having jurisdiction, not understanding the science. We have great scientific tools to enable us to characterize the risks and safety associated with installations, but the authorities having jurisdiction don't have that technical background in many cases. So having policies that enable the deployment of hydrogen technologies is key. One simple example of that is we tend to regulate hydrogen as a chemical rather than as a fuel, whereas natural gas, for example, is often regulated or typically regulated as a fuel, and there's a lot less burden, bureaucracy burden in terms of deploying those technologies. So I think policy is key to enabling the deployments going into the future.
Thank you. And Kat?
Yeah, I just wanted to, I guess, close with that California can't meet its regulatory requirements without a fuel, and that hydrogen is a great option. In my work specifically, I showed that we can have droughts over the state of California for as long as 10 consecutive days where you have far less wind generation than you expect. So in order to have a reliable, robust electricity system, we need some kind of long duration storage, which hydrogen is a great potential option. And these various other sectors that people have brought up throughout the discussion today, heavy duty transport, industries like the steel industry, a fuel is going to be essential in this transition. So relating it back to policy, again, we need policy during this transition period where hydrogen is more expensive so that we can have it when we need it to meet the requirements later on. Thanks.
Thank you so much. I want to thank each of you, David, Hanna, Chris, and Kat, for your wonderful comments, but also for your work, okay? The kinds of research and development things that you are pursuing today are really important for our zero emissions future. I appreciate you spending some time here sharing your expertise and knowledge today. I'm also very, very thankful to CCST for putting this all together and inviting me. Also, I thank you for doing that. I know that hydrogen offers unique zero emissions features that we absolutely need to achieve our policy goals. And I'm hoping that this little gathering that we've had here today will convince all of you that we should invest in this zero emissions future. Thank you.
Thank you, Jack. Thank you to all the panelists. And of course, thank you to everyone who joined us today. Thank you for all of your questions. I know there were some we weren't able to get to, but the good news is that if you want to watch this again, or you have a colleague that wasn't able to attend, we will be posting the recording on the CCST website, along with the one-pager and also the contact information of all of the experts. So I hope if you have additional questions, please feel free to follow up. And keep your eye out for future announcements for upcoming CCST expert briefings. Thank you. Have a great day.
Thank you.
Thanks, everyone.